let's get to some of these problems. Hopefully this gets enough of the ones that we wanted to ask. Is this gonna work for me? I think so. Am I recording? Yeah. All right. I think topic 3, starting with this guy here. Professional sports team evaluates potential players based on speed and strength. And we are told that speed, yep, it's measured by the amount of time taken to run 40 yards. Of course, smaller times is faster. From previous speed data for all players in this position, the times to run the 40-yard dash has a mean of 4.6 and a standard deviation of 0.15, with a minimum time of 4.40. So based on this relationship, is it reasonable to believe that the distribution of this is approximately normal? Well, if I have my bell curve here, we should know the 68, 95, 99.7 rule. If I have my mean of 4.6, if I'm going one standard deviation to the left, I'm subtracting 0.15, which will get me to 4.45. If I go one more, I'll be at 4.3, but we are told our minimum time would be right about here at 4.40. So that would tell us no. Since the lowest point is just over one standard deviation below the mean. Let's see what the AP guidelines said for that. 2011. Yeah, so you'd want to say, I guess you'd want to they'd want you to get the z-score for this and include that in a normal distribution. I guess if you get the normal CDF of that, it'll be less. Let's do that actually. So if I'm doing 4.40 minus 4.60 over 0.15, let's see what we get. Oops, did that wrong. Okay, so that's our z-score. Let's get, if we do the normal CDF, ending at that z-score as our top bound, negative 1.33, with these being standard. Right. There is 9% of the data should be less than that. We don't have that, so it is not a good choice. Okay. With this one, we were told that the strength, on the other hand, it's just measured by how much you can lift in weight. If we have a mean of 310 pounds for what? I guess this doesn't say what you can lift in like what kind of lifting scenario. Calculate and interpret the z-score of someone who can lift a weight of 370 pounds. Well, wouldn't I do 370? Let's remember the z-score formula. It's the point minus the mean divided by standard deviation. 370 minus 310, all divided by 25. Notice that we're not told about this being normally distributed. So we have to be careful with that. Wouldn't this be 60 divided by 25? I can't do that in my head. 2.4. So what I'd say is the amount this person can lift is 2.4 standard deviations above the mean. Let's check the AP on that as well. Yep. Very good. Okay. So it's saying if these for part C, if these are equally important to selecting a player, if I had one player with this running speed and this strength versus another player with these two, which one is better? So all we're gonna do is compare the z-scores for both. We don't know what the distribution is, but that's all we're gonna do. So for speed, we have the mean is equal to, was it 4.6? Let's double check. Standard deviation of 0.15. And for strength, we have mean is equal to 310. Standard deviation is equal to 60. Is that right? Not 60, 25. 60 was another number used there. Okay, so for let's compare each variable first. Let's do speed. So for player A, we do 4.42 minus 4.6 divided by the standard deviation of 0.15. Notice that we want a farther, for speed, we want a farther negative z-score. Wouldn't a lower z-score be a faster person? Whereas for strength, a higher z-score, a higher strength indicates is more desirable. Let's get that z-score. Negative 1.2. For player B, it'd be 4.57. Oh, this is going to be a low, closer to the mean. Minus 4.6 over 0.15. Let's get that. Negative 0.2. So at a first glance, this guy is more desirable. Let's compare the strength, though. So for player A, it would be, I would have 370 minus 310 over this 25. Didn't we do that? Yeah, we did that. So that's 2.4. For B, it'd be 375 minus 310 over 25. So that's going to equal, let's find out. It's going to be close. 2.6. Okay, so with this information, knowing that speed and strength are of equal importance, they are very similar in strength, whereas they are less similar in speed. So if they are of equal importance, you would want to choose player A because he is much faster than player B is, while they are of similar strength. That's all you would do. One thing you can do to like embellish this, which is not required, wouldn't I want to find, in this case, the absolute value of negative 1.2 versus the absolute value of negative 0.2. Then I can add these to the other z-scores so I can get a sum of these things. So I get here 2.8, I'd get here 3, a sum of these things. Hopefully you understand a little bit, 3.6. Because isn't the absolute value of this is more desirable, whereas like just the positive of that is desirable. Okay, next one. What's next? All right. shopping mall has this. I think this is the discrete random variable unit. Shopping mall has 3 ATMs. Because these machines receive heavy use, they sometimes stop working and need to be repaired. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. We got the probability distribution for that. What's the probability that at least one ATM is working when the mall opens? Well, I could either do, whoa, what's going on? I don't like when it does this. Probability that this thing is greater than or equal to 1. Well, that can't I do? Let me see if I get out of here. Try it again. Can't I just do these 3 together? 0.21 plus 0.40 plus 0.24. Those are the probabilities associated with the values when there are at least one ATM. And that gets us 0.85. Another thing that you are really going to want to know how to do, probability of it being greater than or equal to 1 is going to be equal to 1 minus the probability of none. Or let's say, x is equal to 0. So that's 1 minus this guy, which is the same thing. Next, the expected value of number of ATMs working when the mall opens. Expected value you might see as EX, you might also see as mu of x, or just mu. That's just the average. To do that, we do the sum of each individual x times the probability of that x. And just multiply each pair of its number and its probability and add those things up. So that's 0 times 0.15 plus 1 times 0.21 plus 2 times 0.40 plus 3 times 0.24. Let's find those. So this here is going to get me 0. This here is going to get me a 0.21. This here is going to get me a 0.80. This here is going to get me a 0.72. So 0.101 or 1.01. So 1.73. So we can say we can expect on average 1.73 ATM working on a random day, on any random day. Okay. Next one, what's the probability that all 3 are working when the mall opens, given that at least 1 is working? Okay, we have a conditional probability. So let's do some notation here. Probability, whoa, don't do this. Change the color, see if that'll do anything. That it's taking the value of 3 given that it's greater than 1, greater than or equal to 1. So that's equal to, man, this is annoying. The probability that, well, on the bottom, I'm going to have the probability of it being greater than or equal to 1. Is this going to work? And well, on the top, I'd have both. Well, x is equal to 3 and x is greater than or equal to 1. I'm going to save this and like do something else in a minute. I don't know what's going on. Thought I have a strong computer. Well, let's see. wouldn't my denominator be that's greater than or equal to 1? Isn't that this value right here, 0.85? Well, this here, the intersection of these two is just gonna be when there's 3 working. And that's gonna be my 0.24. Like this is, the probability that 3 are working under the assumption that at least 1 is. So that's equal to, well, I needed to divide those things. 0.28. Okay, and then it says, I'm given that 1 ATM is working, if I'm given that more than 1 is working, would the expected value be less than, equal to, or greater than the previous one? The previous expected value. Well, isn't our previous expected value 1.73? But that 1.73 has some probability of none working. If I am restricted to just these 3, and my entire probability distribution now has these numbers, these probabilities are gonna go up. Because what we'd have is 0.21 over 0.85, 0.40 over 0.85, and 0.24 over 0.85. You're not asked to calculate that, but man, this is annoying. But if you are narrowed to the options when it's not 0, you're getting that lower number out of the question. So the answer is, yeah, it would definitely increase. I'm gonna save this and close it. And reopen it. What? Why is this going so slow? Onward. Okay, next one. Each full carton of grade A eggs consists of 1 randomly selected empty cardboard container and 12 randomly selected eggs. The weights are of such cartons have this normal distribution, 840, okay. What is the probability that a randomly selected full carton will weigh more than 850 grams? That's a simple normal CDF problem. Let's do that. So if I'm saying, let's just say if I have my normal distribution with the mean of 840 and a standard deviation of not 12, 7.9. And with the probability of it being greater than, I haven't even defined this x, but being greater than 850, that's just normal CDF. And we do 850 as our low end. Let's put in 10,000 here. And we'll do our mean of 840 and standard deviation of 7.9. Oh, I'm a teacher, I can't talk like that. Let's punch that in. What is it? 840, 7.9. 0.103. Okay. The weights of the empty cardboard boxes have a mean of this, standard deviation of that. Is it reasonable to assume independence? Oh, it is reasonable to assume independence between the weights of the cardboard containers and the weights of the eggs. It is also reasonable to assume independence among the weights of the 12 randomly selected eggs. Okay. Let this random variable x be the weight of a single randomly selected grade A egg. What is the mean and standard deviation of that? Okay. So, we know, let's say x is equal to egg, and let's say y is equal to the box. We know that 12x plus y is equal to the 12 eggs, and the box is equal to the entire thing. So like the expected value of those is equal to 840, and the standard deviation of those is equal to 7.9. So let's see how we can move backwards. Let's get the expected value. Let's define the variable now as 12x. There are the 12 eggs. Wouldn't I take away the mean of the box? The expected value of just the 12x is equal to the 840 that we have minus the cardboard container of 20. So we have the mean of 820 grams. That's our mean. Sorry. Oh, that's the mean of 12 eggs. So then, if I want the mean of one egg, I have 12x here. This is simply a linear operator. I do 820 divided by 12, which is what? I don't know. 68.833. Wait, is it 0.833? Oh no, just 0.33 grams. Standard deviation. So, wouldn't the standard deviation of these 12 eggs, it would be standard deviation of 12x is equal to this 7.9. And I'm taking away the variability of the box. So it would be 7.9 minus 1.2, which is equal to 6.7. So let's go over here. The standard deviation of 12x is equal to 6.7 grams. So then the standard deviation of just a singular egg x is going to be that 6.7 divided by 12. Or wait, did I do this wrong? I think I did it wrong. Yeah, I did this wrong. Yeah, hang on. So I'm gonna erase a little bit. Ooh. Okay. So I'd know that I would do so we'd have to do this Pythagorean style, like 12 squared times the standard deviation of the eggs squared plus this 1.2 squared to get our 7.9. So I need to be able to solve for this standard deviation of x. I'm going to start by squaring things. So I'm going to say 12 squared times the standard deviation of x squared plus 1.2. Well, 1.2 squared is equal to, well, what's 7.9 squared? 62.41. Oops, 62.41. Let's subtract whatever 1.2 squared is, 62.41. $60.97. So I'm going to say 12's, well, this 12 squared is 144. 144 times the standard deviation of x squared is equal to 60.97. Now I'm going to divide by 144. I can talk about this in class, 9 p.m. on a Sunday. .423. When I divide by 144, I get the standard deviation, the variance of the weight of an egg is equal to 0.423. So the standard deviation of the weight of an egg is equal to square root of that, 0.651 grams. Let's check that. I don't even trust myself. And I got one more. 2013. Let's see, if I put in 13 here, will it do it? Nope. What number is it? I got it wrong. That's oh, did I used 1.2, not 1.7. That's what I did wrong. That's what I did wrong. Looks like they did it a little bit simpler, so let's change that. Let's going everywhere. Fix this. I'm just not even erasing for me. What's up? Okay, so this is how they went about it. They said the variance of a box of like the entire box, or let's just say of the entire, yeah, is equal to the variance of the carton plus, well, 12 of the variance of the egg. And what we want is the standard deviation of the variance of the egg. So, let's see. We know the variance of the entire thing is 7.9 squared. That's standard deviation squared. So that 7.9 squared is equal to the variance of the carton. Well, what's the standard deviation of the carton? 1.7. So it's just 1.7 squared plus 12 times the variance of the eggs. Let's get both of these guys. 7.9 squared. That's my 62.41. Let's subtract that 1.7 squared. 59.52. So 59.52 is equal to 12 times the variance of the egg. What they did? Yeah. Wait. They wouldn't do 12 squared here? Squared. I am not sure. I'm gonna go with it. We divide by 12. And that would give us 4.96 is equal to the variance of an egg. So we square root to get the 2.23. I'm going to take another close look at this and see why didn't they square the 12? That's where I differed in two places, right? I made a mistake. I did 1.2. I don't know why they wouldn't do 12 squared. Moving on. An airline claims that there is a 10% probability that a coach class ticket holder who flies frequently will be upgraded to first class. It's independent. That's good to know. Okay, so given this probability, we are asked what is the probability that this person's first upgrade, and you see first upgrade, or the first instance, that's the geometric random variable, will occur after the third flight. So you want to know what's the probability of it happening after the third. So if I'm just thinking about this as a number line, if I want after the third, I don't want the third or less. So I want 1 minus the probability that this thing is taking less than or equal to the value of 3. So I'm just going to do 1 minus the geometric CDF. And I'll put in 0.10, 3. Because this CDF just does the probability of x less than or equal to some letter k. And here you have p and then x there. So let's do that. 1 minus. It's in second bars. Geometric CDF 0.13. 0.729. Now what is the probability that he will be upgraded exactly 2 times in the next 20? Okay, that's the binomial. We have a set n is equal to 20, and we have our x is equal to 2, and we still have our probability is equal to 0.10. So for exactly 2 times, that's the probability of it being exactly 2, we'd say it's the binomial PDF. I think it's binom PDF. 20. So we do NPX there. 20.10. 2. Let's see. Isn't this the expected outcome, right? Because we have NP. 20 times 0.10 is equal to 2. So let's see what the probability of that is. $20.10 2. 0.677. Okay. And now the last thing. They're saying he will take 104 flights next year. Would you be surprised if he receives more than 20 upgrades during that year? Okay, so if there is a set of 104 flights, and I want the probability of being upgraded more than 20 times. I'm gonna save this and close it again. Thought my computer was good. Let's think of it in terms of a number line again. Let's just do 18, 19, 20, 21, 22. If I want the probability of, if he receives more than 20, isn't that those guys? I don't want 20 or less, so wouldn't I do 1 minus the probability of it being less than or equal to 20? That's exactly what I need. You always want to get it into a less than or equal to when you're looking for more than one value. Like, you know, the value associated with more than one outcome. So I do 1 minus the binomial CDF. And I'd put in my n of 104, my probability of 0.10, that's been the same probability, and this value here of 20. Let's calculate that. So wouldn't I put in 104, comma, 0.1, comma, 20. Close it. I'm doing 1 minus that answer. And that has a probability of less than 1%. Equals 0.001. So would you be surprised? Yeah. Probability is low. I'm going to bed. I hope this helped. If you need more help, just let me know.